This second morning session is Professor Adrian Baule from Queensberry University of London, and he will speak about Lévy flights and enhanced tracer diffusions in active suspensions. So please welcome.
Thank you. Yeah. So I thank the organizers for the opportunity to present my work here. And I should emphasize this collaborative work with Kiyoshi Kanazawa, Tomihiko Sano, and my former PhD student, Andrea Cairoli. So the problem I'm interested in is you have a box of a liquid, let's say water, and you have a particle, a micro-sized particle in it. And how can you describe the motion of the particle? So of course, if there's no if there's no other structure in the liquid, but it's only at a certain temperature, you just undergo a normal diffusion process. But now I want to assume that you have other particles within that liquid and they move in a self-propelled way. Okay, so we call them swimmers. So they're active because they move by themselves by some active dissipative process. And in fact, this kind of system has attracted quite a lot of research for the last 20 years or so in the context of active matter. And for example, those are representations of swimming microorganisms. So you can imagine that you have, for example, swimming bacteria or algae, they move in a self-propelled way. And for example, this first experiment is mentioned here, they really looked then at the motion of a particle which is immersed in this liquid and how does it move? Okay, and how can you describe it statistically? It's not Brownian motion. Okay, so the question is, what is this process that is being driven by the interaction between with these swimmer particles? There are two important aspects here. So I'm not sure where the it's here. Okay. So there are two important aspects here. So typically these swimmers move slowly. Okay, this means that it's so-called low Reynolds number swimming, which simplifies some of the mathematical interactions that are behind tracer motion. And I will also assume here that the density is low of these swimmers, which is also quite often satisfied in these experiments. And in fact, so what do you see now if you run an experiment? So it's quite an interesting difference to Brownian motion. Okay, so for example, you see trajectories of this type. You have quite often you see loop-like motion of the tracer particle. If you now measure the diffusion coefficient, it's strongly enhanced compared to the normal thermal diffusion. And it's of course due to the interaction with the swimmers. But how that now actually interacts to give this enhancement is not clear. And there are some theories that simply assume there's some phenological contribution due to the fact you have a density of swimmers and they just interact, but nothing really that goes back to the microscopic interactions. People have also looked at the non-Gaussian exponent parameter and then found a certain scaling regime here that decays with the length over which you observe the tracer displacements. And typically, if you look at the PDFs of the displacements, they have some kind of non-Gaussian tails, but it's not really clear if it's an exponential tail or a power law. So there have been different conjectures about this. Now, from the theoretical side, there hasn't really been any comprehensive work. So as I mentioned, there's this phenomenological flux idea. Then there's also this idea which goes back to theories of interacting particles of the Holtzmark type, which simply assume you have a tracer and you have static swimmers that interact with a certain flow field interaction, but the swimmers don't move. And they can capture some of these non-Gaussian tails in the distributions. But of course, it's not a fully dynamic theory because the swimmers are just stationary. So how do we describe this system? So we make simple assumptions that in order to capture this mathematically, that we describe now these swimmers, they're all randomly oriented in the volume and they move with a constant velocity, which is very typical for these kind of active matter systems. And that there are simply scattering this tracer particles. So the motion of the tracer is simply the sum of the interactions from all these other motions of the swimmer particles. Now the interaction force, in fact, is very complicated. So I assume here that there is, in fact, comes from the hydrodynamic interaction. So it's intermediated by the fluid. And there have been experiments which established that it has then a so-called dipolar form, which simply comes from this intermediation between just one particle and another particle, which moves in a straight line in a liquid. So it will be a very complicated motion. And in fact, just these two body interaction already explains this loop-like motion. So if you just have two particles, one swimmer, it moves straight, this tracer particle will undergo a loop-like trajectory, okay, which is described by this far flow field interaction. And this is now important, and this connects back to this dilute conditions, which I want to assume. In this case, these will be the important contributions to the scattering.
What is NI?
NI is the direction of the swimmer. So they will, I will just assume they have initially some isotropic orientation. So they just move in all directions. Exactly, in 3 dimensions. Yeah, just a vector of size 1. Yeah. And so now how can I describe this? This is, of course, a very complicated problem, right? It's a multi-particle problem, a strongly nonlinear interaction force. There's no way to solve this simply for the tracer dynamics. Of course, you can use it to simulate it, and we'll see later how that compares. So how can we now actually make some progress on the theoretical side? So the key point is now, if you look at now, for example, here's the force pulse that acts on these tracer particles. This is now, these are not typical trajectories. And so one can see that they're kind of dominated by these large pulses, which are essentially those that come from two-body interactions. So of course, in principle, all the swimmers interact with a tracer particle. But since I assume a dilute system, and this is also very similar to, for example, the theory of dense gases, where you also then reduce the multi-body interactions simply to two-body scattering events. Okay, this will be the key. And if you do this, then you can map this process into a much simpler process. So you have here the real microscopic dynamics of these end swimmers. But now I map this onto actually a process of the type which was just being shown, where you have simply a sequence of pulses that occur with a certain rate. Okay, so in here you have to then determine what is the intensity of these pulses that occur, scattering the tracer particle, and within, and also what is now the shape of the pulse. And in fact, one pulse will be determined simply by a two-body interaction event between one swimmer and the tracer. So this intensity, I can determine simply now. The swimmer dynamics is very simple, right? It's just you have some initial conditions, they move in a straight line. So essentially what you want to know is what is the rate per unit time in volume element that the scattering event happens between a swimmer and a tracer. And the scattering event is here simply defined by the fact that it is perpendicular, that the separation vector, so the distance between the swimmer and the tracer, is perpendicular to the direction of the swimmer. And if I do this, I can establish this intensity, and this will of course depend on the density of the swimmers, and this will be something which is then averaged over the initial conditions, which are uniform initial positions in the volume and isotropic orientations of the swimmers. In addition, I need to have the form of the two-body interaction. So this is now just the two-body interaction between the tracer and the swimmer that moves in a straight line. And in fact, here we use an approximation where we solve this ODE by a Picard iteration. And I can show that this is quite a good approximation, in fact, when the distance between the swimmer and the tracer is large. And so, for example, we've compared this with now the force shape from the numerical simulation. This is the simulated time series. And here you have the straight, the black line, which is maybe a bit weak. It approximates this force pulse quite well. And this is really from the approximation to second order by solving this two-body interaction problem for this very complicated nonlinear dipolar force. So this can actually be analytically expressed, which is also the key later on, because we want to understand the scaling behavior of the dynamics in different time regimes later. So we've described here this process. So we've mapped this problem that you have initially swimmers, they move in certain directions. In this problem that you now have a rate of interactions of two-body scattering events. And for this process, you can then obtain all the statistical properties of X simply because this characteristic functional can be expressed in closed form. And then essentially you have to evaluate this expression here. And one can then do this approximately for different delta T regimes. For example, if delta T is small, then you simply recover the case that I mentioned at the beginning where the swimmers are essentially static. Okay, but now you can also go to time regimes where you involve the motion of the swimmers. So what do you see? So first of all, we have here characteristic time scales. So this B star is roughly the effective size of the swimmer. Okay, so when the spatial scales are large, this is the scales I'm interested in. We can also form two time scales, where this is smaller than the other, so which essentially have to do with the fact when is the motion of the swimmers relevant for the dynamics, and also when do the swimmers actually come close to the tracer such that you have a sequence of many collisions. So if you first look at the regime where this delta t is small, so as like the static event, in fact, we capture the same exponent. It comes from the static Holtzmark type theory, and is also very well recovered in the simulations. But now the interesting regime comes when you go to larger delta t. So now the motion of the swimmers becomes relevant. Then you get a change in the exponent, and in fact, the exponent increases. So the tail of the displacement distribution actually becomes wider. And our prediction here is that this is in fact a power law tail of the displacement distribution. So simply now the statistical properties of taking one displacement over certain delta t time of the tracer particle. And how can we understand this? And this is in fact a Lévy flight regime. Of course, in mathematical sense, this would be a pure jump process where you have a power law with some truncation. So truncation comes here in very naturally because of the finite swimmer size. So for example, if you now look at the real force time series, so this is what moves the tracer. Okay, so now if you're in the short time regime, it is essentially static. So everything is smaller than this time scale tau h. But if you now go to larger times where you essentially integrate over all these pulses, you get this effective Markovian regime, which is captured by these Lévy flights. Okay, and we can see here for one that you get an intensity which is overall diverging, okay, in the thermodynamic limit when you go to large system size. And if you look at now, so the size of these pulses, so the integral over these amplitudes, you can show that they essentially scale like a power law, okay? And so this is very interesting here that if you only take the first order in this Picard iteration of the two-body interaction, this will in fact give you a closed loop, okay? So there won't be any effective motion of the tracer. But if you look in more detail and you add now the correction term in the second order, you will get a loop which is almost closed. But this net displacement, in fact, this is distributed like a power law in the distance from the tracer. And this essentially explains this Lévy flight regime that we see here. And this is also, you observe this also in the simulation. So this exponent is quite well captured here. If you now go to get larger times, much larger times, in fact, you can use a central limit theorem argument that the motion of the tracer should revert back to simply Gaussian behavior, simply because then all the swimmers exert multiple collisions on the tracer particle, and this will be effectively like Gaussian. So overall, this theory kind of captures the spectrum of dynamical behaviors that is established from the experiments. So we have this loop-like motion. You obtain the scaling of the mean square displacement, which is just linear in time. You also have these non-Gaussian tails in the displacement distribution. And we can also capture the scaling of this non-Gaussian parameter, which simply comes out if you when you calculate it. So overall, we've derived this process from the microscopic tracer dynamics. And this, in fact, the first, or we believe the first really microscopic model where the Lévy flight dynamics comes out from a physical multi-particle system where the interaction is intermediated by real physical forces. Okay, so it's really kind of the effective dynamics of the tracer due to the scatterings with the set of swimmer events. Now you can look at the exponents. For example, you can ask what is the dimensional dependence of the exponents. So there's a simple dependence of this Holtzmark, the short time regime on the dimension. And also this mu is simply the leading exponent of the force interaction. Okay, so we essentially have a power law interaction due to this far flow field regime. And this in a way gives this exponent in the short time regime. But now this in the Lévy flight regime, so at later times, this exponent will depend on how far is the tracer scattered or is displaced by one loopy motion. And this will be an exponent which is not directly related to the simple exponents in the force law. Okay, so this is something more complicated, but in this case, we were able to evaluate it for this particular hydrodynamic force. Then there's an interesting conjecture that, so now this time scale, which is tau c, so the later time scale when these collision events become important and the dynamics goes back to Gaussian behavior, it's scaled as 1 over rho, so where rho is the density of the swimmers. And you can see that that then, so this time scale becomes larger, the density is low. So essentially this Lévy flight regime is a consequence of the kind of the low density regime, and it captures in a way, so this kind of this Poisson nature of having individual pulses is simply a manifestation of the fact that you have individual swimmers interacting, right? It's not a field-like effect. But this also means that there will be a crossover in the kind of behavior of the tracer particle. If you now imagine, for example, you have these microorganisms and they're actually hunting a nutrient, which is like a tracer particle, then the motion of the nutrient will be very different depending on whether you have a high density of swimmers, of microorganisms, or low density, right? And in fact, this will in fact switch from a more localized diffusion process to one where you have this Lévy flight regime of the tracer, which is very different in counter statistics, of course. I mean, it's of course another topic, what is kind of optimal search in these kind of environments. But it tells you that it might be that, for example, depending on the density of the swimmers, these organisms should change the way they search for these nutrients, these passive traces. And this is everything I wanted to talk about. So thank you for your attention. We have plenty of time for questions, it seems.
Thank you very much for this interesting talk, and I would like to invite people to present questions and comments. Yes.
I raised my hand in the chat.
Really.
Okay. When you look at the swimmers, and what would this situation qualitatively change if you assume somehow that the swimmer after the collision would randomly change its direction?
So actually, I haven't. This is some of the current work that I've looked at in the last 2 years. So you can also develop a theory when the swimmers are moving themselves randomly. Okay, so I mean there's another stochastic process of the swimmers, but you mean just because of the interaction of with the tracer?
No, the question is because if you're after, I mean, the question is if you need recollisions for your theory. No, I mean, if you have one collision and you collide with the same particle later, with the same swimmer later on, you introduce some kind of memory effect.
Yeah.
And if you does your result depends on having this memory effect or not?
Exactly, it depends on not having this memory effect. Okay, so you assume that these interactions are independent because this Poisson intensity, it neglects these kind of memories. So I just assume that from the fact that I have a number of swimmers and they swim in a certain direction, I derive this intensity, and this doesn't contain then any memory effect. So it simply means that you have then independent interactions between the tracer and the swimmer. There was a question by Eli Bakay on the chat, I think. Yeah.
We'll get back to the virtual participants, but anybody in person has a question? Okay, so let's go to virtual participants now.
So I should ask. So
Go ahead.
I can't hear you. Adrian, thank you for your talk.
Can you go? You can speak now.
Okay, thank you very much for the very nice talk. I want to ask a relatively simple question. In the static regime, you have dipoles and you have, I think, I don't know what your dimension is, but it is, I think, 3.
Yeah, it's 3.
So usually you get this Holtz mark from like gravitational objects with charges.
Yes, that's true.
But here it's somehow maybe I didn't really understand why you get this 5/2, because you should get you have it's dipoles, not charges. And another I didn't really understand the 5/3. Is there? You try to explain it, but how would that? I didn't really understand on what exactly it depends, because you say it doesn't depend on D or nu. So on what does it depend?
No, it depends. No, so the whole microregime that you mentioned, this will depend on these numbers like this. You have 1 plus D over nu. So where D is a dimensionality and nu is the leading exponent in the force law. So if you
So
have,
why do you have 5/2? Because you have nu is 3, I think, and d is also 3. So I didn't get it.
no, the nu is different. So for this interaction force. So I mean,
It's not a dipole force? I think you said it was a dipole, so it's
yeah, so this is the leading force here. I have it here at the beginning. This gave like this, so this will be,
okay. It's like a charge. It's like 1/2. Okay, nu is equal to in your case.
yeah, and this exactly. So this will give rise to this 5/2.
So why do you call it dipole? I mean, okay,
This might be from these experimental works, so they call it a dipolar force.
it's more a charge because it's like a gravitational. Okay, okay, but
But then you
why
have the simple relationship, yeah.
why 5/3? Is there a simple? I mean, how would that change if you change the exponent nu? Or
Yeah, this is this relationship here. Sorry, I don't know if you can see this 1 plus d over nu. So this nu is the leading term in the force law. And if you have a different exponent, so if you have, for example, these Coulombic forces which just scale as r to some power nu, so this would be the leading exponent, then you get a relationship like this. So this will determine it for all dimensions and also all exponents.
okay, but
But this can be relatively simply calculated, right? This is the same as the Holzmark theory. So you just put in the force interaction, and then you calculate the leading term, dynamical term for the tracer. But the more complicated exponent is the one that comes from these almost closed loops, where this really depends on the full force interaction between a swimmer and the tracer.
But there could be a regime where you don't have pulses at all because you could have correlations. What I mean is that the force is along very long path in the same direction when you go to very small nu.
Yeah, it could be. But I mean, eventually you have to take the time long enough, right? Eventually since it's just one swimmer, the swimmer will go away after a certain time or kind of be far away. Then that should be a negligible effect after some time. And then
I don't think so, because there is a big difference between short range interactions that you have here and long range interactions, but okay.
So you mean if you get a small enough nu, because it's a very long range, then you should see some different dynamical behavior that.
Of course, if nu is 0, then you're just pushed in one direction all the time, and it's not a pulse effect. It's very different.
But it might be non-singular, right? That limit. It might be a singular limit, right? So it's not. One has to investigate this, yeah. But it's a good point, of course.
Okay.
I would suggest that we have a session from 2 to 3 today devoted for discussions, and this probably will be a very good topic for discussion and much more time. I just wanted to ask if there are more questions or comments. Yes, so somebody wants to ask on Zoom again, so please go ahead.
Yes, thank you very much. So hi, Adrian. So
Hi.
I hope you can hear me. So I wanted to ask 2 short questions. So the first one is related to the approximation of the equation of motion for the tracer. So I get how you go from the extended pulses to but I missed the first piece of the approximation. So it's some slides. Not this one. There is
this one, yeah.
No, there is one where you have 3 pictures and
this one.
not this one.
Okay.
No,
Not this one. Okay.
another. Go ahead. More. Here. Yes.
Okay.
So for the force, yes. So you have this first picture, and then you have this dilute limit. So how do you get from this picture to the 3 pulses? And this is my first question. And my second question is if you have contacts with groups of experimentalists, or is someone doing experiments on this to corroborate the theory?
Okay, yeah, thank you for your question. So in fact, this behavior one can show also more generally simply for this. So when you have direction. So when you have this dynamics here, which is something like a Campbell process, and you can show that at some point this will actually go over into just the white noise shot process. And this is in a way this behavior that you see here, right? So you have a pulse, so you have a sequence of pulses, but if you then go to long enough times, essentially these will be kind of localized pulses, and it then depends on the amplitude of these pulses what the resulting stochastic process is. And in this case, one can see that this should correspond to power law distributed amplitudes, which give you this Lévy flight regime. This is simply from the fact that you kind of initially you only experience for over short times, you just almost have a static effect from the fact that the motion of the swimmers can be neglected. But if you go to much larger times, then it's essentially like you integrate over these individual pulses, which give you this effect like just a normal Lévy process, pure jump process. Is that enough in terms of explanations? Otherwise, your second question, yeah, so we essentially looked at the results that are in the literature, which we thought was nice because we don't have our own experiments that we kind of want to tailor to, but we have looked at results from the experiments. And as far as I know, I have it at the beginning, there are several groups. I don't know about more current experiments, but and for example, this is the data that is shown here. This is in 2 dimensions for which the theory can also be adapted. And as I mentioned, it wasn't really clear this tail whether it corresponds. So some of these early experiments they claimed it would be an exponential tail, whereas in our theory it comes out as a power law tail. And these experiments, for example, they also obtain a power law. And so I'm not sure exactly about more current experiments.
Okay, thank you very much.
Thank you.
Thank you, all the speakers this morning, and thank you, Adrian, for this beautiful talk. And I wanted